6.2 has to now deal with the antiderivative of the reciprocal function and another form of the fundamental theorem of calculus, which I'm going to refer to the fundamental theorem of calculus as FTC. So your essential question, there's a lot here. We're going to go back and we're going to review how do you find the derivative of the ln of x function, and then how do you find the antiderivative of the reciprocal function. So this is the reciprocal function, which you should realize that when you take the, hopefully you remember, when you take the derivative of ln of x, you get the reciprocal function. So probably when you take the antiderivative of this, you're going to get back to the ln of x function. And then how do you apply the derivative of an integral form of the fundamental theorem of calculus? So this is how I'm going to write fundamental theorem of calculus, so we don't have to write it all out. Okay, so let's go back and review the derivative of ln of x. So the derivative with respect to x of ln of x equals 1 over x. And if the input of the ln of x function is something more than just x, remember to chain rule it. If we chain rule it now, right, the derivative of x is just going to be 1. But let's say, for example, I had x squared there. Then I need to multiply this by, for example, 2x. Okay? So always remember that chain rule. Example 1, let's just do one of these, and I'm going to make it a little bit complicated. We're going to find the derivative. So this lesson will have you actually, the first half of it is just finding the derivative. Okay, so for this, I noticed that I have ln of 9x in the numerator, ln of 6x in the denominator, and so a good way to deal with this would probably be to use the quotient rule. So that's what I'm going to do here, quotient rule. Okay, so what I have here now is the derivative of y with respect to x. And I'll take the derivative of the numerator, which the derivative of ln of 9x is really 1 over 9x, chain rule that, so times 9. Okay, and I need to multiply that by the denominator, so times ln of 6x. From that, I'm going to subtract the numerator, ln of 9x, times the derivative of the denominator, which would really be 1 over 6x, and then chain rule it, so times 6, all over the denominator squared. Okay, so simplifying things, these 9's reduce. Let's see, these 6's reduce. All right, so what I'm left with then is ln of 6x over x minus ln of 9x over x all over ln of 6x squared. Okay, so there was a property that we learned about logarithms in an effort to kind of combine these, which actually, let me rewrite that real quick. So that's really ln of 6x minus 9x over x all over ln of 6x squared. Okay. So there was a property that said that if we, it's got a problem. ln of 9x, ln of 6x minus ln of 9x all over x. Okay. Now I think I've got that written properly. Okay, so there is a property that says if we are taking the difference between two ln's, that's really the same as taking the ln of a quotient. So let me write that property over here for you. So if I had ln of x minus ln of y, I could really write that as the ln of x over y. Okay, so that's what I'm going to do here. I'm going to rewrite that so I can simplify it a little bit more. Okay, so this is really going to be the ln of 6x over 9x over x. And then dividing by this is really the same thing as multiplying by 1 over ln of 6x squared. Okay, so really now what I get, this reduces. So I'm really ending up with the ln of 2/3 over x times the ln of 6x squared. And that's about as reduced as I'm going to get this answer. I could definitely plug ln of 2/3 into my calculator, but this is an exact answer, so this is good. All right, let's do another one of those. Just remembering how to do the derivative or take the derivative of the ln function. So if my function is y equals sine of ln of x, then my derivative of y with respect to x, well, the derivative of sine is cosine of ln of x. And then I need to chain rule that, so now I need to do the derivative of this inside piece, and the derivative of ln of x is just 1 over x. So really what we get is we get cosine of ln of x, right? That's my inside function, all over x, just multiplying straight across. So now let's explore the actual integral of the reciprocal function. So now going backwards. Given 1 over x, how would you find the integral of that? Okay. So if I want the integral, this is the indefinite integral, of 1 over u du. Okay, so I'm using u instead of x, and there's a reason for that. And this is where we're going to get into some u substitution. This will be the ln of the absolute value of u plus c. Now, why are we saying the absolute value of u? So let's recall what the ln function looks like. Okay, if you were to graph the ln function, remember it's the inverse of the exponential function, right? So the exponential function looks something like this, b to the x. It goes through this point, 0, 1. Oops, I'm off the screen, sorry. Okay, so that's the exponential function. So the ln function is the inverse of that. Okay, I should actually not even write it as just exponential. It's the inverse of the natural exponent, right? E. And with the inverse, if you remember, the inverse function is always, we just switch x and y, right? So I know that a point on this graph is going to be 1, 0. Okay, and it's reflected over that line, y equals x. So the graph of the natural log function, and really any log function, is going to look similar to this. So notice none of my inputs for this function are negative, which is why we need an absolute value there. You should not be if you try and put a negative input into an ln function, you're going to get an error in your calculator. Let's do an example. So we will evaluate, and I'm going to use a thing called using u substitution. This is a way to potentially make thinking about these problems and the anti-chain rule easier, okay? So I'm going to expose you to it here. You don't have to use it. You could do this without using u substitution, but it is a helpful tool. Okay, so the first one we're going to do, I'm going to do the integral of x squared plus 1 over x cubed plus 3x dx. Now, of course, in all of these problems, if there's any algebra you can do to make to simplify this before you get started, that's going to work in your favor. But I noticed here, like I see that there's an x in the denominator that can be factored out. There's nothing to reduce it with in the numerator. There's not a common factor, so I'm not going to do that. What I am going to do is thinking to myself, well, can I rewrite this so that it kind of looks like a reciprocal function? And I can. Really, this is the same thing as 1 over x cubed plus 3x times x squared plus 1 dx. Okay, so here's what I'm going to do. I'm going to let u equal this junk down here, because unfortunately it's not as easy as just this, right? And they never will be. So I'm going to let u equal x cubed plus 3x. And if I do that and I take the derivative of that, so du is 3x squared plus 3. Now that's going to help me work with just this piece right here. And remember, this probably came from that chain rule, okay, when they originally took the derivative. Okay, so let's think about this. I'm just going to take this piece right here, and I'm going to rewrite it as the integral of 1 over u du. Okay, so notice how I have a value for u, right? I just rewrote this complicated thing, okay? And I also have a value for the derivative of u, okay, which is this thing right here. Okay? All right, so this really becomes then 1 over u. Well, 1 over u is going to become ln of u, right? The integral of 1 over u is going to be ln of u. Okay? And it needs to be the absolute value. Okay? Plus c. Now, the question is, in this problem, I also have this x squared plus 1. Well, notice what I got when I had my du. I had 3x squared plus 3. And really, all I want is x squared plus 1. So what do I need to do to du to get just this x squared plus 1? What I should be thinking to myself is, if I divide this by 3, I will then get x squared plus 1. So really, right, because this is where that chain rule of the derivative comes into place. Now, how do I get this to equal this? What I need to do is I need to divide by a third, right? Or sorry, not divide by a third. I need to multiply by a third or divide by 3. So I'm going to multiply this by a third. Okay, so now what I'm going to do is I'm just going to take what originally was my u, and I'm going to plug it back in where I see u. So this is really 1/3 ln of the absolute value of x cubed plus 3x plus c. Okay, so that is our final answer. Oops. Now, how could I have done that without u substitution? Okay, because maybe u substitution is not helpful for you. So different people like it different ways, and some people find u substitution really helpful, and others find it very confusing. So, had I not used u substitution, okay, oops, that's not how you spell u sub. USB. So with no u sub. Okay, so the way that I would have thought about this with no u sub was, again, I would still break it up like this. But the first piece, I would think to myself, well, that's got to be the ln of whatever that input was. Then what I would do, as I've said many times before, I'll go over here to the side. I'm going to take the derivative with respect to x of that. And if I do that, what I would see was that I would get 1 over x cubed plus 3x. Then I would chain rule that and realize that I would then multiply by 3x squared plus 3x. And then I would notice, hey, these are not the same things, right? This is not the same as this. I need to divide by 3. So I need to divide by 3, which I would then do, which is exactly the same thing as multiplying by 1/3, and then always the plus c. So that these two answers match, but I came to them in different ways. Okay, so this is me not using u sub, but me thinking back and forth between the taking the antiderivative and then taking the derivative and saying how do they match, which is exactly what was happening here. That's the exact same thing. Okay, it just simplifies it when all you have to do is think about u instead of thinking about all of this junk. Let's try another one. So how about we do the integral of x squared plus 1 over, oops, I lied. It's x plus 1, not x squared plus 1. X plus 1 dx. Okay, so using u sub, or actually, before I do that, let me go ahead and rewrite this. I'm always going to rewrite this as a reciprocal function. So I see that this would be 1 over x squared plus 2x times x plus 1 dx. Okay, so thinking about this using u sub, I'm going to let the stuff in the bottom here be my u. So then the derivative of u would be 2x plus 2. And then I will compare it, du with what's over here. Right? Okay, so I'm really taking the integral then of 1 over u du. Okay, so du needs to match what's here. Well, what's the problem? Du doesn't match, right? These three things don't match. So what am I going to have to do in order to get my du to be this? Okay, I'm going to need I'm going to need du to be divided by 2 or multiplied by a half. So really I can say, well, this is the same thing as 1/2 ln of the absolute value of u, just taking the antiderivative of the reciprocal function, plus c. And then I can go back and I can plug things in. This is 1/2 ln. Now we said u was going to be what was originally on the denominator, x squared plus 2x plus c. Okay, so that is your final answer. I'm now going to switch gears and talk about the derivative of an integral form of the fundamental theorem of calculus. But before I do that, I want to explore it a little bit. So let's see, I give you g of x equals the definite integral from 1 to x, which you haven't really dealt with having an x in your limits of integration yet, cosine of t dt. Okay, so if I take the integral, well, what did I take the derivative to get cosine? I must have had sine, right? So this would have been sine of t evaluated from 1 to x. Okay, and if I do that, this is really sine, plugging in my upper limit, this is really sine of x minus sine of 1. Okay, so really what we can think of this as being is sine of x minus, now sine of 1 is no longer a function, it's a constant. So minus some constant. Okay, so think about that, or remember that. Okay, we'll come back to that in a second. Let's do h of x then. So I'm going to do integral from 3 to x of cosine of t dt. Okay, so the integral, well, what did I take the derivative of to get cosine? Sine. So it would be sine of t evaluated from 3 to x. Okay, and so when I do this, I really get sine of x minus sine of 3, which is really sine of x, some function, minus some constant. Okay, so what happens then if I take the derivatives of these? Right? So what happens if I take the derivative of sine x minus some constant? Okay, so let's go ahead and say, if I take, since g of x equaled this, what is g prime of x? Well, g prime of x then will just be cosine of x. And h prime of x, yeah, that's right. And h prime of x, again, just taking the derivative of sine, I'm going to have cosine of x minus, well, 0 really, right? Because you take the derivative of a constant, you get 0. Okay, so hopefully you're seeing a pattern here. If I am taking the derivative of my integral, where my limits of integration went from some number to some value that is a variable, what's going to end up happening is you're going to have this constant in the end. So really all you need to do, this is actually super cool. Notice how this limit, this upper limit, is not the same as this variable. Okay, if somebody asks you then to take the derivative of this integral, all you really have to do is plug x in for t, right? It's just cosine of x. Okay, same thing here. So if we ask you to take the derivative of h, right? Because h is really an integral. So here you're taking the derivative of an integral. So you're undoing each other. They undo each other, right? Derivatives and integrals are opposites of each other. Okay, they are inverses of each other. So they undo each other. So if I asked you to take the derivative of h, and I gave you this, all you had to do then was say, okay, well, I know that there's going to be some constant in there that's going to become 0, so really all I need is that upper limit of integration plugged in. Okay, so let's formalize that. So this is the fundamental theorem of calculus, derivative of an integral form. So if g of x is equal to some constant, that's the lower limit, and your upper limit is some variable that is different than the input variable here, then I know that if I take the derivative of g of x, I am just going to get f of x. It's that simple. Okay, remember a is a constant. That has to be true. All right, so let's do examples. So let's take the derivative with respect to x of, from 3 to x, sine of 3t dt. Okay, all I have to do is, again, if I took the integral of this, I'd get cosine, but then if I took the derivative of that, I'd get back to sine. Right, so this is really going to be sine of 3x, sine of 3x, our final answer on that. The next example we're going to do is the derivative of the integral from -4 to x squared. So I'm throwing in a little curveball here, and notice it's not just x anymore, it's now x squared. Okay, and this is going to be what you're plugging in. Okay, of the quantity t cubed minus 5 raised to the 4th power. All right, so if I take the derivative of an integral, they just basically undo each other. I'm doing it with respect to x. My input here is x. So really I'm left with x squared which then is raised to the third power, minus 5, and that whole thing to the fourth power. Okay, so now it's important. This is important. This is our inside function. And what do we do when we're taking the derivative with our inside function? That's right. We basically chain rule it or take the derivative of it. So I need to multiply that by 2x. So my final answer here is 2x times, that becomes x to the 6th minus 5, quantity to the fourth power. And that's my final answer.